All right, this video is about Coulomb's law and lattice energy. By the end of this video, you should be able to know what Coulomb's law is and be able to use it. You're also supposed to know what lattice energy is. It relates to how ions are attracted to each other. Ions have charges. That's what Coulomb's law is all about. And you can follow in your textbook. Those other definitions are going to be in this video. You might want to look in your glossary or look them up online or remember from Chem 1 what they are. All right, first thing is to talk about what lattice energy is. Lattice energy is just the attraction or measures the attraction between ions in an ionic compound. Remember, those are big crystals. So this ion, this positive, is attracted to all the negatives around it. And in order to be able to turn into a gas, you have to break all those attractions. So lattice energy is just the energy that you need to put in to turn it into gas phase. Coulomb's law is the law that we use in physics and in chemistry to talk about the attractions between charges. There's two things that are important. The charge part is important. Those go in the numerator. And the distance between the charges is important. That goes in the denominator. You don't need to worry about what K is. I just want to point out this nice bond energy diagram that we've been talking about. That the reason you need to put lattice energy in, let's say the negative thing's at the origin, the positive ion is going to be right at this dip here in the figure, and lattice energy is the energy that you need to give it to get it out so that it can go on its merry way. All right, so let's look at some examples. All right, so I have a few examples up here where we can use lattice energy to talk about why the lattice energy numbers are the way they are. You don't really need to know the numbers, you just need to know the trends. All right, we're going to look at these first two examples. Mg here is 2 plus and F is minus. You know that from the periodic table. Mg here is 2 plus and O is 2 minus. All right, if we plug those numbers into the lattice energy diagram, well, the Q plus is going to be 2 plus in both equations. So Q plus is 2 plus, Q plus is 2 plus. But the negative one is different. That's going to be -1 here, and it's going to be -2 here. We don't know what R is, but we don't care. It's the same, or roughly the same. Well, you guys know that 2 times 2 is going to be 4, or in this case, -4. And 2 times -2 is going to be, 2 times -1 is going to be -2. Well, -4 is bigger than -2. In other words, the lattice energy here is bigger than the lattice energy here. All right. So in other words, to summarize, lattice energy increases as Q increases, as you increase the charge. All right, in this second example, the charges are the same, but the distances are different. If you remember from Chem 1, lithium and fluoride are both in the first row of the periodic table. They're not the same size, but the real one that we have to look at is the distance between the fluoride and the chloride. Chloride is huge. Chloride's much bigger than fluoride because it's the next row down on the periodic table. It's the next energy level. You have a lot more electrons. The R here from the center of the atoms is going to be a lot bigger than the R there. So when you plug those in the denominator, we don't even need to know what QQ is in each example. So for that one and for that one. Let's say this distance is 1, well this distance is 2. Which one's going to give you a bigger lattice energy? In this case, it's this one. Lattice energy is going to be bigger here because you're dividing by a smaller number. And yes, in fact, we see that trend is true. So as the R gets smaller, as the ions get smaller, the lattice energy gets bigger. All right. This crazy diagram is pretty much a way that we can calculate lattice energy. It ends up that it's really hard to experimentally calculate lattice energy, but we can go and put together a lot of delta H's of other processes that we do know to figure out what the lattice energy is. I'm going to point out to you that you know this first process down here at the bottom. We know what this process is called. We learned about it in class. Look at the things on the left and look at the thing on the right and try to figure out what's that called. What's that process when you turn atoms from their standard states into this kind of thing? What's that process called? All right, I'm also going to point out to you that you should know what it's called when you turn just lithium solid into lithium gas, and you should know what it's called when you turn lithium gas into a lithium ion that's gas. In other words, what happened to the lithium to turn into an ion? You know the name for that. When you put energy in or take energy out to do that, you know the name. All right, you probably, unfortunately, don't know the name to turn a fluoride molecule into a fluorine ion. Excuse me, fluorine molecule to fluorine ion. That process is when you break a bond and one electron goes with each atom. All right, that's actually called dissociation. But you should know the name for when a fluorine atom turns into a fluoride ion, when an extra electron goes in. You should know the name for that. And finally, you should know the name for when the solid ionic compound turns into the gaseous ions. You should know the name of that. All right, I'm about to unveil them. These are them. Hey, ionization energy, sublimation. This one didn't show up. This is heat of formation. And plain old lattice energies over here. Oh, and dissociation and electron affinity are there. All right, next thing that I didn't show was the signs of these numbers. I showed the energies required to do them, either the energy that goes out or the energy that goes in. I want you to spend some time thinking about what are the energies. Are they positive or negative? Do you have to put energy in to do the process, or does energy come out when you do the process? In other words, are you going to need to break an attraction? That requires putting energy in. Or do you form a new attraction? That's when energy comes out. That's when you release energy in the form of heat, usually. So think about all those numbers. Think about whether the sign should be positive or negative. Pause the video right now and do that. Did you pause the video? All right, I'll start again. So, sublimation, heating something up, turns it into a gas, that's positive. Ionization, you know ionization energies. You need to knock an electron out of an atom. That requires breaking the attraction between the electron and the nucleus. That's also positive. Electron affinity, on the other hand, is negative because you're forming a new attraction. When the electron goes into the atom, it falls into the well. It releases energy. In dissociation, you need to put energy in to break the bond, to break the attraction between the two fluorines in the bond. Finally, heat of formation. When you form the thing, you make a new attraction, so that's negative. In lattice energy is positive, but the arrow actually is drawn in a negative way, so it actually ends up being negative. And through the wonderful power of Hess's law, if you take all the numbers from this and you add them all up, you get that, which is essentially the lattice energy, or the opposite of the lattice energy. Why do we care? Well, this shows one reason why we care. As lattice energy goes up in general, melting point goes up. Why? Well, if the lattice energy is the measure of the attraction in the ionic compound, then you need to add more and more heat to break that attraction, to melt it. So that's reflected in the third bullet here. You need to break that attraction if the lattice energy is high. It needs more heat. You have a higher melting point. Next one, lattice energy lets metals be ions. What does that mean? Well, we just saw on the last slide that to turn sodium into sodium ion, you need to knock out an electron. You need to put in energy. The delta H is going to be positive. Well, why doesn't the electron just fall back in? You would get energy out. It'd be exothermic. That sounds like a good thing. It would happen. Except the sodium is so attracted to the other ion that it's with that the electron doesn't have anything to offer. The sodium is so deep in the well with the chloride, the sodium's like, I don't care about you, electron, anymore. I've got a much bigger energy attraction with the nonmetal, with the other ion. Lattice energy is also related to solubility. If a sodium is hanging out, a sodium ion is hanging out with a chloride ion, and a water comes along, well, yeah, actually, sodium is more attracted to the negative end of the water molecule, the oxygen end, because water's polar, than it is to chloride. So it says, chloride, see you later. On the other hand, if an oil molecule comes along, oil's not polar, sodium's way more attracted to the chloride than it is to the oil. So pretty much it's not going to be soluble. So the higher the lattice energy, the less soluble something is.